Okay, so in the previous lecture, we introduced C-star envelopes of star algebras. Let's briefly recall the definition. So suppose that A is star algebra. So roughly speaking, a C-star envelope of A is a kind of universal C-star completion. Formally, the definition looks as follows. The C-star envelope of A is a pair consisting of a C-star algebra C-star of A and a star homomorphism theta from A to C-star of A, which has the following universal property. So for each C-star algebra B is a C-star algebra, and each star homomorphism phi from A to B, there exists a unique star homomorphism psi such that this diagram commutes. So in other words, we have the following natural bijection between the set of all star homomorphisms from A to B and the set of all star homomorphisms from C star of A to B for each C star algebra B. Okay, so this is the formal definition, which easily implies that if a C star envelope of A exists, then it is unique in the obvious sense, that is, it is unique up to unique isometric star isomorphism over A. That is a star isomorphism which makes the respective diagram commutative. I don't claim that this object always exists. This is not the case. However, we discussed at the previous lecture, we discussed some sufficient conditions for the existence of a C-star envelope. In particular, we proved that if A is generated as a star algebra by the matrix entries of some family of unitary matrices over A, then the C-star envelope of A exists. Let's also recall some terminology and some notation related to universal C-star algebras. So we denote by F the Fourier algebra generated by some family of letters xi and yi, where I runs over a set big I. So we make F into a star algebra by introducing an involution as follows. And we choose an arbitrary family Pj of elements in F, that is a family of free polynomials. And we denote by I, well, I is not I, but a K. We denote by K a two-sided star ideal generated by the family Pi. Generated by the family Pj. And we define the universal C-star algebra, the universal unital C-star algebra generated by the family xi with relations Pj to be the C-star envelope of the quotient of F modulo I, modulo K. And this algebra has the universal property that you have another unital C-star algebra, say A, and a family of elements in this C-star algebra indexed by the same set big I and satisfying the same relations. That is, if we substitute our elements to the polynomials Pj, then we get 0. And in this situation, we have a unique unital star homomorphism from this algebra to our algebra A, which takes the generators xi to the elements ai. So this is the universal C-star algebra given by generators and relations. Okay, let's now look at some examples of C-star envelopes. Example 1. Let A be the algebra of Laurent polynomials in one variable t. So this is a short notation for the algebra of Laurent polynomials. And we define an involution of this algebra as follows. So T, the generator T, becomes a unitary element. Clearly, this involution uniquely extends to the involution of the whole algebra. So what is the sister envelope? Well, here's an answer and an exercise at the same time. The sister envelope of this algebra is the same as the universal sister algebra generated by a unitary element. And this algebra is isomorphic to the algebra of continuous functions on the circle. So here T, bold T, denotes the unit circle on the complex plane.
So the A is just a group algebra of integers.
Yeah, exactly. This example easily generalizes to several variables. Example 2. Let A now be the Laurent polynomial algebra in finitely many variables T1 to Tn. And again, we introduce an involution on this algebra in such a way that the generators Ti are unitary. And similarly to the previous example, we can show that the sister envelope of A is the same as the universal sister algebra, the universal commutative sister algebra generated by n unitaries and commuting unitaries, U1 to Un. And this algebra is isomorphic to the algebra of continuous functions on the n-dimensional torus, Tn. Okay, example 3. Let now A be the polynomial algebra in one variable, or we can also take the algebra of Laurent polynomials in one variable. But the involution now is different. We define an involution in such a way that T becomes a self-adjoint element. So what can you say about the sister envelope of A? It's natural to call this sister envelope the universal unital sister algebra generated by a self-adjoint element. But it turns out that this algebra doesn't exist. There is no universal sister algebra generated by a self-adjoint element. Example 4. Now let's suppose that A is the algebra determined by two generators P and Q and the following commutation relation. The commutator of P and Q is I1, where 1 is the identity of the algebra. Well, this is a very classical object. This is the Weil algebra, one of the most important algebras in quantum mechanics. We make it into a star algebra. Namely, we define an involution in such a way that P and Q are self-adjoint elements, which is also very natural from the point of view of quantum mechanics. Q corresponds to the position of a particle, and Q is P is the momentum. So in this case, in contrast to the previous example, the sister envelope does exist. but it is trivial. It is equal to 0. In fact, this is a standard exercise in functional analysis to show that such a commutational relation is impossible in any unital Banach algebra. This easily implies that the only submultiplicative norm on the Weil algebra is identically 0. And as a corollary, there is the sister envelope is 0. And this example also explains why we have to use unbounded operators if we want to do some quantum mechanics. Okay, now example 5. This is the so-called Topless algebra. So let's consider the universal C-star algebra generated by an isometry. An isometry is an element U such that U star U is 1. Note that, observe that in this case, again, the C-star envelope does exist, because if we take an arbitrary C-star seminorm of U, then it is less than or equal to 1. Actually, it is exactly 1 by the C-star axiom. So our results from the previous lecture readily imply that the C-star envelope exists. And it can be described explicitly as follows. This algebra is isomorphic to the C-star subalgebra of the algebra B of O2, or the algebra of bounded operators on a separable infinite dimensional Hilbert space, generated by the right shift operator. Generated by the right shift. This is not obvious, but this is true, and this is the so-called Coburn Theorem. Coburn's theorem. You can consider this as a not so easy exercise. Okay, example 6. Example 6 is the so-called two-dimensional quantum torus. Quantum two-dimensional torus. And another name for the same algebra is the rotation algebra. So suppose that theta is a real number, an arbitrary real number. So we define the quantum two-dimensional torus to be the universal C-star algebra generated by two unitaries, U and V. U and V are unitary. And the following relation, UV equals the following number, VU. So again, since U and V are unitary, the C-star envelope exists. And it is called the quantum two-dimensional torus, or the rotation algebra. Let's observe, by the way, that this algebra in some sense can be interpreted as a deformation of the algebra of continuous functions on the torus. Because if theta is 0, then U and V commute. And it follows from example 2 that this algebra is nothing but the algebra of continuous functions on the two-dimensional torus. This follows from our example 2. In general, this algebra looks a bit like something abstract, like an abstract object. So we define it as the universal C-star algebra. But there is an important special case where theta is irrational. And in this case, we have the following explicit description of this algebra. This is an exercise. If theta is irrational, then a theta is isomorphic to the C-star subalgebra, the C-star subalgebra of the algebra of bounded operators on the L2 space on the circle, L2 on the circle, generated by the following two operators, U and V, where U is the multiplication by the coordinate. So U is given by the following formula. And V is the rotation operator, which acts as follows. It's very easy to check that this C-star subalgebra generated by these two operators, if you take the C-star subalgebra generated by these two operators, then these operators U and V, big U and big V, satisfy the same commutation relation. So in any case, we always have a surjective homomorphism from A theta onto this C-star subalgebra. So the point is that if theta is irrational, then this homomorphism is bijective. And so this is an isometric star isomorphism. By the way, this exercise also explains the name of this algebra, the second name for this algebra. So this is the irrational rotation algebra. Okay, example 7, which is very short and which was actually we have already observed this at the previous lecture. Namely, if we take two C-star algebras A and B, then we can always take their algebraic tensor product, which is a star algebra, and then take the C-star envelope. And this C-star envelope is nothing but the maximal tensor product of A and B. And actually, this is immediate from the definition. If you look at the definition of the maximal C-star tensor product, you will see that this is just a special case of the notion of a C-star envelope. Example 8. Suppose now that G is a group, a discrete group. Actually, this example can be generalized to locally compact groups, but for simplicity, let's assume that G is discrete. So let's take the group algebra of G. CG is the group algebra, and we make it into a star algebra as follows. So all elements in G, which can be viewed as elements of the group algebra, will be unitary. And we give the following definition. The group C-star algebra, or more exactly, the full group C-star algebra of G, is by definition the C-star envelope of the algebraic group algebra defined in the previous line. Usually we use the word full in order to distinguish between this algebra and the reduced group C-star algebra, which was defined some time before some lecture, a few lectures ago. By the way, here's another equivalent definition of the same algebra, and at the same time an exercise for you. the full group C-star algebra can also be defined as the C-star envelope of the L1 group algebra of G. So the L1 group algebra is usually bigger than the algebraic group algebra, but the C-star envelope will be the same. So this algebra is useful because if we look again at the definition of a C-star envelope, we will see that that each unitary representation of G on the Hilbert space uniquely extends to a star representation of the full group C-star algebra. What is the relation between the full and the reduced group C-star algebras? Well, the relation is given by the following picture. So we take the algebraic group algebra. So the algebraic group algebra is a subalgebra in the L1 of G, and L1 of G, there is a canonical homomorphism from L1 of G into the reduced group C-star algebra. So we get a homomorphism from here to here. And by the universal property of the full group C-star algebras, we have a unique star homomorphism from the full group C-star algebra to the reduced group C-star algebra. So this is a surjective star homomorphism. It is surjective because it is the identity map on the algebraic group C-star algebra, which is dense in its completion. And we know that each star homomorphism between C-star algebras has a closed image. So this implies that this star homomorphism is surjective. In general, this is not an isomorphism. And in fact, we have the following criterion, which I formulate without proof. This homomorphism is bijective, so it is star isomorphism. If and only if G is amenable. Which means that there is an invariant mean on little L infinity of G, a bounded linear functional on little L infinity of G, which is normalized, positive, and shift invariant. Okay. Well, probably that's all I wanted to tell you about C-star envelopes in the general case. We'll come back again soon to C-star envelopes when we discuss concrete examples of compact quantum groups. In fact, this is the main reason why we discussed C-star envelopes. Okay, so our next goal is to introduce compact quantum groups. Well, let's begin with some motivation. We already know the first, that is commutative Galvanic theorem, which implies that there is a duality and anti-equivalence between the category of compact Hausdorff topological spaces and the category of commutative unital C-star algebras. Also, there is a similar result in algebraic geometry. The result is a categorical form of Hilbert's Nullstellensatz, and it states that there is a duality, an anti-equivalence between the category of affine algebraic varieties over the complex numbers and the category of commutative unital algebras, which are finitely generated and which don't have nilpotence. According to the philosophy of non-commutative geometry, an arbitrary non-commutative algebra, it is very useful to consider an arbitrary non-commutative algebra as an algebra of functions on a quantum space, that is, on a non-commutative space, which doesn't actually exist. Under this actually there are several types of non-commutative geometry, and different types of algebras correspond to different types of geometries. In particular, non-commutative unital C-star algebra can be interpreted as the algebra of continuous functions on a quantum compact topological space. So what we want to do is to define algebras of functions on quantum groups. Well, to define them, let's first recall what a group is. Well, a group in general, a group is a set with an extra structure, that is the multiplication, which satisfies some natural axioms. Also, there is a notion of an algebraic and a fine algebraic group, or a compact topological group, which is a topological group with some extra structure. To define quantum analogs of groups, to define quantum groups, let's first of all try to dualize the definition of group. That is, let's try to write the definition in terms of algebras of functions. For convenience, we start not with groups, but rather with semigroups. So suppose that G is semigroup, and let f of G denote an algebra of functions on G. Let's look at two special cases. We can look at different algebras of functions on G. So we were mostly interested in the following two cases. In case one, G will be an affine algebraic semigroup. And f of G will be the algebra of regular functions on G. For example, we can take the algebra, the general linear group, GL and C, or a special linear group, or the multiplicative semigroup of all square n by n matrices. And case two, which is especially interesting for us. In case two, G is a compact topological semigroup. And f of G is the algebra of continuous functions on G. Let's now observe that in both cases we have a suitable tensor products. Namely, in case one, if we take the algebraic tensor product of O of G by itself, then we get the algebra of regular functions on G cross G. This is a standard algebraic result. And the isomorphism takes each elementary tensor, f tensor G, to the function given by the following formula. And in case two, we have a similar isomorphism if we replace the algebraic tensor product by the, say, minimal C-star tensor product. In case two, we know that the minimal C-star tensor product of C of G by C of G is isomorphic to the algebra of continuous functions on G cross G. And the isomorphism is given by the same formula. So let's consider these cases simultaneously. So let A denote O of G, and the symbol of the tensor product will be the algebraic tensor product in case 1. And in case 2, A will be the algebra of continuous functions, and the same symbol will denote the spatial or minimal C-star tensor product in case 2. Okay, so G is a semigroup, so there is a multiplication on G. So let's draw the following picture. Multiplication on G will be denoted by little m. So we can dualize this map by applying the functor f, which is the irregular functions in case 1 and the continuous functions in K2. And we get a map from A to A tensor A, which will be denoted by delta, and which is given by the following formula. Here we identify A tensor A with the suitable algebra of functions on G cross G. Now the multiplication on G is associative, so it is associative semigroup. And the associativity can be expressed by the following commutative diagram. This is M cross 1. This is 1 cross M. And this is the multiplication. So the fact that the multiplication on G is associative is equivalent to the commutativity of this diagram. And when we dualize this diagram, we get to the following picture. This is A. This is our map delta. This is again delta. And here we can take either delta tensor 1 or 1 tensor delta. And this diagram is commutative. So the commutativity of this diagram is equivalent to the commutativity of this diagram. So these pictures lead us to the general notion of a co-algebra. By definition, co-algebra is a pair, A delta, where A is a vector space, as usual over the complex numbers, and delta is a linear map from A to A tensor A. Such that the above diagram, I mean this diagram star, such that the above diagram commutes. So the map delta is called the co-multiplication. On A. And the above axiom that this diagram commutes means that in this case, we say that delta is co-associative. The commutativity of this diagram means that delta is co-associative. Okay, and one more definition. Suppose now that A, delta is a co-algebra. We say that it is a bi-algebra if A is not just a co-algebra, but it is also a unital algebra. And delta is an algebra homomorphism. So in this case, we say that A is a bi-algebra. And delta is a bi-algebra. Delta is also unital, a unital algebra homomorphism. And finally, if A is a sister algebra, if A is a unital sister algebra, the tensor product sign is now interpreted as the minimal sister tensor product, and delta is a star homomorphism. Then we say that A is a unital sister bialgebra.
Why this tensor product?
Well, we could also take the maximal one. Actually, if we take the minimal one, there is only informal explanation that if we have a unital sister bialgebra with respect to the minimal, with respect to the maximal tensor product, it will also be a sister bialgebra with respect to the minimal one, because there is a natural map from the maximal to the minimal, and not the other way around. So potentially, if we use the minimal sister tensor product, then we have a potentially bigger class of objects, and this seems to be the only reason. But in fact, for many concrete examples, when we discuss concrete examples of quantum groups, we will see that they are nuclear, and so we can replace the minimal one by the maximal one. So in this case, we say that A is a unital sister bialgebra. Morphisms between bialgebras and unital sister bialgebras are defined in an obvious way. Morphisms of unital sister bialgebras are defined by the following picture. So if A and B are unital sister bialgebras, then their morphism is a unital star homomorphism. Say phi from A to B, such that the following diagram commutes. This is the co-multiplication on A. This is the co-multiplication on B. And this is phi tensor phi. So unital sister bialgebras form a category. Okay, now it follows from our previous discussion that we have a functor. First of all, we have the following natural example. Natural example, if G is a compact topological semigroup, then C of G is a unital C-star bialgebra. And similarly, in the pure algebraic case, if G is an affine algebraic semigroup, then the algebra for regular functions, O of G, becomes a bialgebra. A unital bialgebra, of course. But when we speak of bialgebras, we usually assume that they are unital. In fact, it's easy to show that each commutative unital C-star bialgebra arises in this way. So we have the following theorem, which is actually a version of the Gelfand-Meinrad theorem adapted to the case of bialgebras. So suppose that A and delta is a commutative unital C-star bialgebra. And let G denote the maximal spectrum of A. So let's look at the following picture. We take the co-multiplication and we apply the spectrum functor to the co-multiplication. So we obtain a continuous map from the maximal spectrum of A tensor A to the maximal spectrum of A. And this is delta star. Now the maximal spectrum of A is G. And since A is isomorphic to is canonically isomorphic to C of G, so A tensor A is isomorphic to C of G cross G, and the maximal spectrum of this algebra is canonically isomorphic to G cross G. So we get a continuous map from G cross G to G. So let's denote it by M. I claim that G, together with this operation M, is a compact topological semigroup. Compact topological semigroup. And moreover, the Gelfand transform of A, which takes A to the algebra of continuous functions on G. We know that this is an isometric star isomorphism, but actually it is an isometric star isomorphism of C-star bialgebras. This unital C-star bialgebra isomorphism. Well, the proof is very easy. So let's suppose that delta is assumed to be co-associative. And since the Gelfand-Meinrad correspondence is an equivalence of categories, which takes products to tensor products, we conclude that M is associative. This follows from the Gelfand-Meinrad theorem. So G is indeed a semigroup. which is obviously compact because the maximal spectrum of a unital C-star algebra is compact. And now it's rather easy to show, this is a simple exercise for you, that gamma is indeed a C-star bialgebra isomorphism. A C-star bialgebra morphism. So it is an isomorphism by the Galvanic theorem. Okay, so this completes the proof. Let's now observe the following. You have two compact semigroups, G and H. And a semigroup homomorphism, phi from G to H, continuous homomorphism. Then the induced map, phi dot, from C of H to C of G, is not just a star homomorphism, but it's actually a homomorphism of unital C-star bialgebras. Unital C-star bialgebra. A unital C-star bialgebra homomorphism. So we have a functor from the category of compact semigroups to the category of commutative unital C-star bialgebras. And it immediately follows from our previous results that this functor is an equivalence. We have an equivalence of categories. So the first category is the dual of the category of compact semigroups. And the second one is the category of commutative unital C-star bialgebras. And the equivalence is the same. It's just we use the same functors as in the Galvanic theorem, namely the functor C and the functor max. So this follows from our previous results. Okay, the picture is very nice, but this is not exactly what we wanted to do. So actually what we want to do is to prove a similar result for compact groups, not semigroups, but groups. So our next goal will be the following. We would like to construct a certain category which will be denoted like this. This will be a subcategory in the category of unital C-star bialgebras. Such that the commutative part of this category corresponds precisely to the category of compact groups under the Galvanic correspondence. Probably you have already guessed that CQG means compact quantum groups. How could we construct such a category? Well, probably some of you are already familiar with the notion of a Hopf algebra. At this point, I'll not give the formal definition. Roughly, a Hopf algebra is a bialgebra, A delta, equipped with an additional structure, namely equipped with two maps, epsilon and S, where epsilon is an algebra homomorphism from A to the complex numbers. And this homomorphism is called the co-unit. And the linear map S from A to A, which is called the antipode of A. Well, the basic example is the algebra of regular functions on an affine algebraic group. In this case, the co-unit is just the evaluation of the identity. And the antipode is responsible for the inversion map. So the antipode is given by the following formula. In the general case, the co-unit and the antipode are defined as maps satisfying some natural axioms. And although I will not give you a precise definition at the moment, we will need it somewhat later. So we can try to do the following. First of all, we observe that if we look now at the algebra of continuous functions on a compact topological group, then we can define a co-unit and an antipode on this algebra by the same formulas. So we can try to introduce the notion of a unital Hopf C-star algebra, similar to the notion of a Hopf algebra, with obvious C-star modifications. That is, by replacing the algebraic tensor product with the minimal C-star tensor product. In some sense, this approach works. So we will get the required equivalence between these two categories. But nevertheless, this approach turns out to be very naive. If we define compact quantum groups in this way, then we must throw away many natural examples of compact quantum groups, including the probably the most standard and classical example, namely the quantum SU2 group introduced by Voronovich. It turns out that for many concrete examples of compact quantum groups, including the quantum SU2 group, there is no co-unit and no antipode. Or more exactly, they do exist, but they are unbounded. And they are defined not everywhere, but only on a suitable dense Hopf star subalgebra. So our strategy to defining compact quantum groups will be as follows. The strategy was suggested by Voronovich. We will try to give, first of all, we will try to give an equivalent definition of a compact group, which doesn't involve explicitly the identity and the inversion map of our group. And after giving such a definition, we dualize this definition. And finally, we arrive to the general notion of compact quantum group. Okay, so let's now try to give an equivalent definition of a compact group. Suppose that G is a semigroup so we'll need the following definition. A subset I of G, a non-empty subset I of G, is called an ideal of G if it satisfies the following conditions. So the definition is similar to the definition of an ideal in a ring. So these inclusions hold for each element X in G. And one more definition. We say that G is a semigroup with cancellation. In Russian, полугруппа с сокращением. If the following properties hold, the equality x1y equals x2y implies that x1 equals x2. And similarly, the equality yx1 equals yx2 implies that x1 equals x2. So G is a semigroup with cancellation. You can always cancel y from on the left or on the right in such equalities. Clearly, each group is a semigroup with cancellation, but not the other way around. So the set of natural numbers is a semigroup with cancellation, which is not a group. We have the following result from topological group theory. Suppose that G is a compact topological semigroup, with cancellation. When G is a topological group. Of course, the compactness assumption is essential here, because we can take, for example, the group of natural numbers, which is a semigroup with cancellation, but which is not a topological group. So to prove this result, we do the following. We take an arbitrary element, little x, in G, and let H denote the closed sub-semigroup of G generated by X. Closed sub-semigroup of G generated by X. And let I denote the intersection of all closed ideals of H. The standard compactness argument implies that I is non-empty. This is an exercise for you. So roughly, we have to show that I the family of all closed ideals satisfies the finite intersection property. So the intersection of any finite family of closed ideals is non-empty. Then the compactness argument implies that the intersection of this family is also non-empty. Okay, so this is the smallest closed ideal of H. If we now take an arbitrary element y in I, then we have the following equality: yi equals I. Well, indeed, it is contained in I, but yi is also easily seen to be an ideal. And since I is the smallest closed ideal, it follows that yi is also yi equals I actually. Okay.
How do we get that yi is closed?
yi is closed because this is the continuous image of a compact set under continuous map. Okay. So this implies that this equality implies that we can find an element, there is an element little e in I, such that ye equals y. Now we do the following. We take an arbitrary element z now in G. We multiply this equality by z on the right. And we cancel y from the left by using the cancellation property. And so we see that Ez equals z. Okay, so now take an arbitrary element w in G. And we continue the same trick. We look at this equality. We multiply it on the left by w, and we cancel z from the right. And we see that we equals w. And so finally, we see that E is an identity. Of G. So our semigroup has an identity. Okay, let's now show that each element is invertible. So we come back to our original element little x. So little x sits in H. And since E is an identity, we have the following equality. We have xe equals x. But on the other hand, E sits in I, and I is an ideal of H. So these properties imply that x belongs to I. X belongs to I, because I is an ideal. Okay, let's now look again at this formula. So for each element in I, we have this equality. So we'll now substitute x here, and we see that xi equals I. And in particular, this implies that there is an element little y in I, such that xy equals E. Now we use the cancellation property once again. So we multiply this by x on the right, and we cancel x on the left. And we see that yx equals E. So we conclude that x is invertible. And since x was an arbitrary element of G, we conclude that G is a group. This is almost the end of the proof, but not exactly, because in the definition of a topological group, we also require that the inversion map is continuous. So why is it continuous? Well, actually, this is very easy. We already know that G is a group. So this implies that the following map, the map from G cross G to itself, which takes each pair xy to xy, is a continuous bijection. So by compactness of G cross G, this is a homeomorphism. So this implies that the inverse map, which takes xy to x inverse y, is continuous. But the continuity of this map easily implies that the map which takes x to x inverse is also continuous. So G indeed is a topological group. Okay, so this completes the proof. So we see that each compact semigroup with cancellation is a topological group. This is our theorem 2. Okay, and now let's try to dualize the cancellation property. That is, to write the cancellation property in terms of the algebra of functions on G, or the algebra of continuous functions on G. We introduce some notation. Suppose that A is an algebra. And suppose that S1 and S2 are two subsets of A. Then we denote by S1, S2 the linear span of all elements AB, where A runs over S1 and B runs over S2. Now we have the following result, theorem 3. Suppose that G is a compact topological semigroup. And let A denote the algebra of continuous functions on G. And we denote by delta the canonical co-multiplication on A. Given by the following formula. Then the following conditions are equivalent. Condition 1, G is a topological group. And condition 2, the following two sets, delta of A multiplied by 1 tensor A and delta of A multiplied by A tensor 1. So these are two subsets in the tensor product, and they are dense. In the minimal tensor product of A by itself. Okay, so let's try to prove this result. First of all, let's show that 1 implies 2. Suppose that G is a topological group. So what is delta of A multiplied by 1 tensor A? This easily follows from the definition of the co-multiplication. So delta of A multiplied by 1 tensor A is the linear span of all functions of the following form, of all functions which take xy to f of xy, g of y, where f and g are continuous functions. And similarly, the second subset, delta of A multiplied by A tensor 1 is the linear span of all functions of the following form. They take xy to f of xy, g of x. And again, f and g run over A. So let's now observe that if G is a topological group, then both these sets, both these subspaces, are actually star subalgebras, satisfying the conditions of the Stone-Weierstrass theorem. So these subspaces are actually star subalgebras. Satisfying the conditions of the Stone-Weierstrass theorem. Well, this is very easy. It's more or less obvious that they are star subalgebras. And they contain the function which is identically 1. So to show that they satisfy the conditions of the Stone-Weierstrass theorem, we must show that separate the points. They separate the points of G cross G. This is more or less immediate. If we have, say, 2 points, x1, y1, and x2, y2, so then if the second coordinates are different, then we can take f to be identically 1, and we choose G in such a way that G separates y1 from y2. And in the case where the second coordinates are the same, but the first coordinates are different, we let G be identically 1, and we choose f in such a way that f separates x1y from x2y, which is possible because x1y and x2y are different. So this shows that the first subalgebra separates the points, and a similar argument shows that the second subalgebra also separates the points. So by the Stone-Weierstrass theorem, they are dense in A tensor A. Okay, let's now prove the converse statement. 2 implies 1. To show that G is a topological group, we will show that G is a semigroup with cancellation. Okay, now suppose that x1y equals x2y. If we now look at this first formula, it follows that for each function in this subalgebra, for each A in delta of A multiplied by 1 tensor A, we have the following equality. H of x1y equals h of x2y. Well, indeed, H is a finite linear combination of functions of this form. And each function of this form, when we apply it to x1y or x2y or x2 and y, so we get the same numbers. So this holds for each h in this subalgebra, but this subalgebra is dense by assumption. And so we have the same equality for each h in tensor product. So the same holds for each h in A tensor A, which is the algebra of continuous functions on G cross G. But this algebra separates the points. Of course, the algebra of all continuous functions separates the points. So we conclude that x1 equals x2. And similarly, by using the second subalgebra, we show that if if yx1 equals yx2, then we necessarily have x1 equals x2. So now applying theorem 2, we conclude that G is a topological group. And this completes the proof. Okay, so now we're ready to define compact quantum groups. By definition, a compact quantum group is a unital C-star by algebra. Unital C-star by algebra. A delta such that the subspaces delta of A multiplied by 1 tensor A and delta of A multiplied by A tensor 1 are dense in A tensor A. So this definition is due to Voronovich. Okay, so we have an obvious example, which is immediate from our previous theorems. If G is a compact group,
Я вам на всякий случай напомню, что сейчас 16 часов.
Ой, Маш, спасибо. Буквально вот последний пример и закругляемся. So if G is a compact group, then C of G is a compact quantum group. And by combining this with the Galvanic theorem, we have the following corollary. We have an equivalence of categories. The dual of the category of compact groups is antiequivalent to the category of commutative compact quantum groups. Okay, so that's all for today. Of course, this is not the only example of a compact quantum group. There are many interesting non-commutative examples. And in the next lecture, we first introduce the basic example, the quantum SU2 group. And then we will show that this example fits in a rather general picture of compact matrix quantum groups. So compact matrix quantum groups were introduced also by Voronovich a bit earlier than the general notion of compact quantum group. So we'll discuss some concrete examples of such objects. And our next goal will be to show that each compact quantum groups has the so-called Haar state, which is a natural non-commutative analog of the Haar measure. Okay, so that's all for today. Thank you.
У меня вопрос. Получается, для коммутативных C-звезда биалгебр вот это определение, это то же самое, что если бы мы через алгебру Хопфа наивно делали или нет?
Да, для коммутативных то же самое. Для коммутативных то же
есть
самое.
мы можем... ну, да, мне кажется, я даже понял, почему.
Ну да, ну там потому что у алгебры CSG всегда есть антиподы, коединица, которые понятным формулам задаются, и можем просто, если они есть, то мы можем их проиграть обратно, грубо говоря, да, посмотреть, что они индуцируют на максимальном спектре, ну и получить на выходе компактную группу. То есть на уровне коммутативных мы получаем то же самое. Но, как я уже сказал, тут, значит, все в том, что для некоммутативных-то, конечно, формально их можно рассмотреть, но мы получим нечто не очень интересное. То есть мы получим некий класс биалгебр, в который не входит квантовая SU2 и не входит практически ничего интересного. Ну, то есть что-то входит, но очень мало чего. Поэтому и приходится вот таким образом выкручиваться и придумывать альтернативные определения.
А нам придется изучать, как устроен неограниченный там антипод и все вот это?
Вы знаете, посмотрим по времени. Мне, конечно, хотелось рассказать вот про вот эту вот плотную подалгебру Хопфа, состоящую из маточных элементов непроводимых представлений, и там будет видно, что это антипод. Ну, по крайней мере, на уровне конкретных примеров это точно мы обсудим, там, что как это выглядит на уровне квантовой SU2, а для произвольных компактных квантовых групп, ну есть надежда, что все-таки успеем. Вот, что действительно есть, что это на самом деле один из таких базовых результатов этой науки, про то, что у любой компактной квантовой группы есть некоторая замечательная плотная подалгебра Хопфа, и на ней уже действительно, на настоящей алгебре Хопфа, там действительно определены и антипод, и коединицы. Просто они, как правило, оказываются неограниченными, и поэтому не продолжаются на всю нашу цистерциевую алгебру.
А база из функционального анализа для этого получается теория неограниченных операторов, да, которые
Нет,
физики любят.
это не используется практически. То есть это там где-то уже дальше используется в каких-то более продвинутых разделах теории квантовых групп, обычно не компактных, а локально компактных. Вот. А то, что они определены на плотной подалгебре и неограничены, ну, это факт, но сама по себе теория неограниченных операторов при этом никак не используется.
Ладно, понятно. До свидания.
До свидания. Спасибо.
Спасибо, до свидания.
До свидания.